Well, hello. Things look a little bit different, don't they? Well, it's quarantine for you. I was able to pre-film a whole bunch before I had to come back here, but this is technically my second set, but I took all my stuff up to grad school, so it's kind of bare. Anyway, I'm the classical nerd, and today we're talking about set theory, a crazy world where minor and major chords are exactly the same, but it's not a system designed to handle tonal harmony at all. In fact, the term chord doesn't even exist in set theory. It's got a bad reputation as something that's super duper math heavy, and that's not really easily understandable by someone who's accustomed to these standard analytical approaches. But as I always tell people, it's actually easier than most of those standard analytical approaches because there are no exceptions. All you have to be able to do is count. You can count, right? Good. I thought so. Just checking. Before we get into the meat of set theory, let's talk a little bit about analytical methodology. The analysis part of music theory that most students are taught and are familiar with has its roots in common practice functional triadic harmony. You probably know this as Roman numeral analysis, and it's pretty good for most types of tonal music. But once composers started abandoning tonality or including more ambiguous harmonies in their music for whatever reason, this analytical approach begins to break down. And other approaches like Schenkerian analysis or Neri-Riemannian analysis also have their shortcomings because they're fundamentally used to describe tonal or at least triadic music. Schenkerian analysis tends to look at the large scale, the deep background of very specifically tonal pieces, and also breaks down when you're looking outside of that system. Whereas Neri-Riemannian analysis doesn't look at the big picture so much as it looks at very small voice leadings between different chords. What the standard Roman numeral analysis as well as the Neri-Riemannian and Schenkerian approaches all have in common is that they're for tonal triadic music. Like, that's their purpose. And set theory goes beyond that and ignores the idea of triads altogether. What matters here from a historical perspective is that the use of atonality immediately led to a new system of musical organization, the tone row, which is the fundamental part of Arnold Schoenberg's 12-tone system. Schoenberg wanted his music to rigorously avoid a key center, so he made sure he ran through this row in different permutations, such that no note sounded more often than another. If he stuck to this plan to the end of the piece, he'd use each pitch the same amount of times. Thus, even the sharpest ears couldn't pick out a central pitch. He thought of the tone row as his theme equivalent, whereas his pupil Anton Webern wasn't as interested in the whole row per se. Webern took the time to chop up the row into little sections, which he made sure were self-similar to one another. And here's where we're really getting to the meat of set theory. Set theory is the practice of dividing music, predominantly atonal music and then usually serial music, up into chunks of 3, 4, or 6 notes, which are then known as sets. These groups, trichords, tetrachords, and hexachords respectively, are then analyzed not in terms of their pitch content, but rather their absolute intervallic content. That is, set theory seeks to understand the intervallic relationships inherent in these sets, and it's not super focused on what the pitches are. It's weird and it's counterintuitive because most analytical approaches, you're looking at the pitches. You're figuring out what pitches are important and what pitches aren't, and you're trying to distill that into something that makes sense on either a small, medium, or long-term scale. And set theory doesn't really do this. And there's a lot of information overload when people are just learning about set theory, so there's this steep learning curve. But the great thing is that it's super consistent, which is more than you can say about literally any other analytical system I can think of. So first off, why 3, 4, and 6? The answer is a purely mathematical one. These go into 12 an even number of times. So usually composers who are cognizant of set theory and its rules and the intervallic comparisons you can make with it, chunk their rows, if they're using tone rows, up into 3 groups of 4, 4 groups of 3, or 2 groups of 6. Occasionally you'll see other groups of 5 or 7, but these don't go evenly into 12, so it's not as common to see them. Now I keep mentioning that intervals are super important in set theory because it's hard to get across to people sometimes that the pitches are not super important. You use the pitches as a reference point to understand the intervals, but you're freely manipulating these pitches in a way that is not usually done in any context other than set theory. One of the big things that confuses people at first is that sharps and flats usually mean different things, and in set theory they don't. You could play me a dominant 7th chord or a German augmented 6th chord, and without hearing the following chord or seeing the score, I would have no way of knowing which one it is. This is a form of ambiguity that set theory lacks. Set theory says that these chords are exactly the same thing. So we have to understand how set theory handles notes. We still have to be able to refer to pitches in our analysis, but because there is now no difference between D flat and C sharp as there would be in tonal music, we have a number-based system, which starts at 0 and runs through 11. Starting from 0 is weird, I'll grant you, but it'll make sense soon. From a practical standpoint, it maximizes the information we can pack in. Think about it. Each of the first 10 notes is identified by a single integer. For 10 and 11, we can substitute T and E. This keeps everything consistent. One character is now one unit of information, if you will. These, though, should not be thought of as pitches. These are pitch classes, and they repeat infinitely. A pitch in set theory is like that note, like that individual hertz, like 440 cycles a second. Like that is a pitch. It's a very scientific approach to it. Pitches aren't really used in set theory. Pitch class is. This is why the classic example is a clock face, where 10 and 11 become T and E, and 12 becomes 0. It's an easy and quick way to visualize the distance between notes. So let's say you have an F sharp and an A. But because this is set theory, you don't say that's an F sharp and an A. You'd say that these are pitch classes 6 and 9. Once we get these numbers, the cool thing is that we don't need to do this on a staff. Because we've converted these to numbers, we can see that because 9 minus 6 equals 3, this is interval class 3. Looking at pitch classes is a way of converting your notes into a format that can be mathematically manipulated. As mentioned, the point here is all about intervals. I don't think this is exactly what Debussy was talking about when he said that the music was the space between the notes, but I'm rolling with it. So, interval class. To me, this is the critical component of what set theory is all about. So, you know how we had a difference between pitch and pitch class? There's a similar distinction between interval and interval class. The interval is the number of half steps between two given notes. It doesn't matter how far apart they are or how close together they are, and you're also taking direction into account. Whereas interval class is completely devoid of direction, and you're compressing it not just to within an octave, but also you're inverting it such that it's either a tritone or smaller. Again, a lot of information, but let's go through the difference in an example. Let's take again this F sharp and A, except instead of being arranged in this nice minor third layout, let's say the A is an octave from the bottom of the piano, and the F sharp is above middle C. This is a plus 33 interval, measuring up from the A. But if we put everything within an octave and then inverted it, you would have this minor third again. This is important because there are only 6 interval classes. 1, 2, 3, 4, 5, and 6. IC6 is the tritone, and anything larger than a tritone inverts to something smaller than a tritone. Perfect fifths and perfect fourths are both IC5. There is no such thing as an IC7. This is only possible because we don't care about direction. And no, octaves are not a thing in set theory. It's the same pitch class, so it's the same note. It compresses to a unison, and there's no IC0. To recap, every pitch is assigned a unique character between 0 and 9, and then T and E, which can then be arranged on a clock for visual aid. The distance between these pitch classes in their smallest possible format is the interval class. If you've got that, now it's time to move on to trichords. Let's take a look at Alberto Ginastera's Piano Sonata, second movement, Presto Misterioso. Within the first two measures, we have a complete 12-tone row, and given the meter, I think it's fair to group these into trichords. For now, let's hone in on the first 3. D, B flat, E flat. Convert this to integer notation and you get 2, 10, and 3. We've definitely got to compress this, so the first step is to put these in order. 2, 3, 10 is much better. But when you're dealing with trichords, you've got to make sure they're in their smallest possible form. That is, the distance between the outer notes needs to be as small as possible. 2 to 10 is a distance of 8. Reordering it to go 3, 10, 2 leaves us with a distance of 11. But 10, 2, 3, now there's a solution. This is where you have to get the clock involved. If you can only move clockwise, 2 to 10 is 8 hours, 3 all the way around to 2 is 11, and 10 over to 3 is 5. 5 is the smallest number we've come up with so far, which tells us that ordering the notes as 10, 2, 3 is the smallest possible form. But we're not done there. This tells us the notes involved, and with a little bit of math, the intervals between them. But we could have had a set that went 11, 3, 4, and it would have the exact same intervals. So how are we going to distinguish? Well, if you're comparing two sets, what is set theory all about? Intervals. You compare them by their intervals. So our 10, 2, 3 set and our imaginary 11, 3, 4 set both have the same intervallic content. You do have to prove this in some way, which is where 0 finally comes roaring back in to save the day. Let's say we add 2 to our set. This brings us to 12, 4, and 5. But there's no such thing as 12. It's the same thing as 0. So by adding 2, which is merely transposing the whole set up so that the first number equals 0, we can create a unified standard to compare disparate sets. This is akin to a level playing field because it allows the numbers involved to more clearly represent their intervals. You can figure out that 10 to 2 is interval class 4, but if you see the numbers 0 and 4, you don't have to do that math. You see, because one of the numbers is already 0. This process is basically a conversion from pitch class to interval class. But wait, we're not actually done yet. In order to make sure we're comparing things correctly, there's one more step involved, and that's called packing left. Basically, you run the set forwards and backwards, and if it's not a symmetrical set, one of these is going to take precedent over the other. This is an extension of the idea of compressing everything down to the smallest possible form. 0, 4, 5 describes the intervals, yes, but it describes them in a certain order. It describes a major third and a minor second, which added together form a perfect fourth on the outside. But here's the thing, we actually get the same exact information if we run the set backwards. So we have to have a tiebreaker. Breaking out our clock, and this time running it counterclockwise, because we're going backwards, 5 to 4 is 1, and 5 to 0, i.e. 12, is, well, 5. 0, 4, 5 is equivalent to 0, 1, 5. This is ideal because it reduces redundancy. Every combination of notes can be broken down in this fashion, and you need to keep your smallest intervals on the left side, or packed left. This is merely a standardization method. The result of this method is called the prime form. Think of it as the lowest common denominator. This packing left is why in set theory what we know as the major triad doesn't actually exist. And even if it did, it wouldn't be called a major triad because in set theory, chords are not known as chords, they're known as simultaneities. If you want to describe a major triad as a major triad, it would be in root position because that's the fifth on the outside as opposed to a form of sixth, which you'd get in first or second inversion. 0, 4, 7 describes this, but 0, 4, 7 isn't packed left. I mean, if we run the set backwards, we get 0, 3, 7. This is the prime form. And 0, 3, 7 is in fact a minor triad if you spell it out. This happens because set theory breaks music down to its intervals, and both major and minor triads contain a perfect fifth, a major third, and a minor third. But the minor third is the smallest interval, and it has to be represented first. The only difference is how these intervals are stacked. So this has clear references to Neo-Riemannian theory, Harry Partch's ideas of otonality and eutonality, and even negative harmony, if you're familiar with that. You've probably got at least two questions. One is the practicality of it, like what is it good for? And the second is, isn't there an easier way to do this? Well, there is an easier way to do this if you're good at visualizing things and moving things around in your head, and I'll get to that in just a second. But I do want to look a little bit more long-term and talk about the practical applications of this. And for that, let's jump back into the Genostera. The second beat of the first measure, spoiler alert, this one also boils down to an 0-1-5 set. Coincidence? Definitely not. The next measure uses the 6 notes that he hasn't used yet, because it's a 12-tone row, and these are both 0-1-6 sets. The value in set theory is to boil down the intervallic content of small chunks of music so you can see exactly how a composer is divvying up a 12-tone row. It's not just about coming up with an ordered set of 12 notes, it's about constructing them in a way that their intervallic content in these little groups is self-similar. So now the quick and dirty way to do this. Alright, this is music theory after dark, come on. Okay, so how do we know that these sets are 0-1-6? I'll take the first one. F, F sharp, and B. Let's not worry about converting integers just yet. Play around with this and just look at it. Which one is the smallest interval on the outside? F, F sharp, B is the ordering that does this. You can just already visually see it's packed left, so check plus. Now if you think of F as 0, there's one half step going to F sharp, so that's 0, 1, then 2, 3, 4, 5, 6 to get to B. 0, 1, 6. Easy. The basic principle also applies to tetrachords and hexachords and really any other set of notes up to 12. The issue is that you have to reorder the notes, and sometimes there are more tiebreakers you have to do because you're just not looking at the leftmost interval, but maybe the second leftmost interval, to try to figure out which one is the smallest possible prime form. So, sit back, relax. You think we're done, right? Well, the good news is that this is the biggest part of the learning curve. If you get this down, you basically have set theory down. But we need to talk about some more advanced principles, which I think are really cool and really worth knowing, so stick around. One of the things I also want to mention is why we pack left. It is fundamentally an arbitrary thing. You could easily do the same thing but pack right. But it's necessary to do this, otherwise sets with identical intervallic content, which is what we're looking at, the intervals, would look like they're two different sets. 0, 1, 6 and 0, 5, 6 are going to look like two different things when their intervals are the same thing. The principle of packing left specifically is the brainchild of Alan Forte, a music theorist who published his book The Structure of Atonal Music in 1973. In this book, Forte also went beyond prime form and categorized all possible prime form sets with something called a Forte number. Forte numbers don't really have that much of a practical analytical purpose, to be frank, because you're not saving a whole lot of time by saying 520 when you could just say 0, 1, 5, 6, 8. Unless you've memorized his classification system, it's not a practical way to communicate because you have to go running to his catalog to find out what interval you're talking about. But the Forte numbers are useful in the sense that they rigorously categorize every possible combination of notes up to the full chromatic set, which in set theory is known as the aggregate. And this is something that allows us to study the hidden gems possible in the mathematical intricacies of 12-tone equal temperament, specifically something called Z-relationships, which I think are really cool and really worth knowing. But in order to understand that, we have to understand another concept called the interval class vector. An interval class vector analyzes the prime form of a set in terms of its absolute intervallic content, in a different way than the prime form does. Basically, what the interval class vector does is it looks for all possible interval classes, 1, 2, 3, 4, 5, and 6. It figures out how many of them there are, and it places that at that position within the vector. Let's do an example. Let's take a tetrachord, for instance. 0, 1, 3, 5 seems pretty nice. What we're doing here is comparing each note and scanning for the presence of each interval class. The number of those that we find will be the number we put in that place in the vector. So first we have to look for interval class 1, the minor second. We only have 1, which is 0 to 1. So 1 is going to be our first number in the interval class vector. Second is interval class 2, of which there are 2. There's this 1 to 3 and this 3 to 5. Now looking for interval class 3. We have 1, the 0 to 3. Interval class 4, that's 1 to 5. 5 minus 1 is 4, so instant interval class right there. Next is interval class 5, for the perfect fourth. We have that 5 on the end, so bingo, we have 1. And finally, no interval class 6, so that's 0. This means that the interval class vector of the 0135 set, which is Forte number 411, is 121110, representing which intervals are present within the confines of the set and how many of them there are. We have to be good at looking at interval class vectors and understanding them if we have any hope of understanding Z-relationships, which are the coolest thing in set theory by my estimation, but are not always easily explained. And knowing the interval class vector is the key to understanding what these things are. Now, let's take a different tetrachord. 0, 1, 4, 6. When you break this down to its constituent intervals for the interval class vector, which I'm not going to run through in rigorous detail here again, you end up with 6 consecutive 1s. There are only 6 intervals in here, and each one is a different interval class. This makes this set something that's actually pretty unique. This is the all-interval tetrachord. Except, this is not the only possible all-interval tetrachord in prime form. Consider 0, 1, 3, 7. This is also an all-interval tetrachord because the interval class vector is precisely the same. As a result, they kind of sound similar, and we can point to the interval class vector as a theoretical understanding of exactly why they do. This is a Z-relationship, and why this is a Z-relationship is because you can't invert and transpose your way from 0146 to 0137, which makes sense because they're fundamentally different prime forms. They're not the same when viewed from a structural perspective, but when you boil them down to just what intervals they've got and how many of them they've got, they're the same. This is why 0146 is classified as 4Z15 in the Forte catalog, and 0137 is 4Z29. That Z indicates there's something special with these sets. It stands for zygotic, which wasn't the original name of these things, but has stuck for some reason. Frankly, I don't quite know why, but they're cool, so I'm going to accept it as fact. Understanding set theory is not just a critical component of analyzing much atonal and serial music, but it's a critical component of, I think, appreciating this style of music as well, because it is designed to be very heady and intellectual and mathematical. But it's a broad enough system, and it's a consistent enough system, that you can use the same approach to understand the heavily self-referential and self-similar tone rows of Anton Webern to the dense and hard-to-unravel music of Elliott Carter. It's the most objective and frankly only way to analyze any kind of atonal music, and it's not just used by theorists. You'd be crazy to think this wasn't on the minds of the composers as well. Elliott Carter, for instance, did something similar to the Forte numbers in his own catalog. When you're coming from a Roman numeral analysis perspective, or even a Schenkerian model, the idea of doing analysis by looking at intervals and basically doing addition and subtraction and really basic pre-algebra in a base 12 system seems like it's not super applicable, but yet it is. Because there are no exceptions or quirks, it's a really interesting and, I think, a really refreshing way of doing analysis. I mean, so long as you are willing to absorb a lot of terminology, but if you made it this far, you did absorb a lot of terminology, so